Hello, it's July 1st, 2023. We're in Physics as Information Processing in the second discussion. So, thanks all for joining, and we'll see who else comes in. If you're watching live, feel free to write questions in the live chat, and I'll relay them onwards. So, Ander, thanks, and it would be awesome to begin with a little bit of some overview and some points that you wanted to get to.
Yeah, thank you, Daniel. So good morning, everyone. So if you would start by bringing up a bit goal, what Chris spoke about last time. So I have a few slides that I singled out so now we're getting to a reformulation of quantum theory in terms of reformulation of opposed to a dynamical theory. And as we've talked in previous sessions, we need to think a little bit philosophically about what the ontology of measurement entails. So Chris last lecture started with these three basic ingredients. So an action, that's number one, a thing to ask about. This is the qubit, the physical degrees of freedom that we need to perturb in some way to ask a question. And then finally, a semantics, a language that makes sense, a context that makes sense of that information that we gather. So I should say, number one, that came up in the first session when I can't exactly remember, but at some point we talked about what is information, and we came up with we brought up a definition that goes something like this. It's an ISA-dash. It's differences that make a difference. This is Chris told me, I can't remember who first coined this dash, but I think it's quite old, at least early 70s. Anyway, so number one, basically, takes care of that part, right? If I want to gather some information, I need to perturb a system somehow, so I need to act. And this is literally in units of actions, right? So units of energy times time. And he provided the example of rhodopsin, right? Which is apparently near optimal from a quantum perspective. This is mechanically what goes on in your eyes as light comes in. And this is literally the difference that makes a difference in your brain. The second part were the physical degrees of freedom. So recall that we had a boundary. Okay, so this theory of quantum mechanics as measurement necessarily breaks down the system into a bipartite system with a boundary, and you are in a boundary which are a lot smaller than the degrees of freedom of A and B, at least in terms of the dimension of the Hilbert space. And the boundary immediate change or
Sorry, can you repeat, Ander?
Repeat what? Sorry.
Just last 30 seconds.
Yeah. So this second ingredient is boundary. The physical medium in which this information exchange occurs, where the physical degrees of freedom, the qubits, are arranged, and these are physically perturbed in order to mediate that difference that makes a difference. So we can think of this dually as either preparing those qubits or decoding those qubits. And then finally, there was the notion of the reference frame. Okay, so this theory necessitates a free choice of the agent of a reference frame, and physically what this amounts to is a free choice of a measurement axis for those qubits. So we can think of measuring z spin in those qubits on the boundary. So that requires a free choice of that axis, and this amounts to your reference frame, the context in which those measurements are performed. On one extreme case, we have that if those references are perfectly aligned, then the exchange of information is is noiseless. There was it somewhere over here, I think. I can't quite recall. But generically, these two reference frames of Alice and Bob, A and B, are not exactly the same. They get to choose the reference frames. I think it's all the way on the bottom, actually, right? So they can be aligned. If they're aligned, they are exchanging noiseless information, right? There is no randomness. If they are not, superposition onto states, and that's when you're going to get, probabilities in the outcomes, trivial probabilities. So far, so good.
Yes.
Okay. So I have a few more comments of the main things. Okay. It'll take me a few minutes, and then we can chat back and forth. Perhaps this slide is the most interesting, important. I remember this is where I asked the question myself, because I still, it's not easy to wrap your head around what's going on here. So we said that measurement and preparation are completely dual pictures. So this is going to be expanded on in the next lecture. But a direct corollary of that is that if you prepare, Chris said it in similar terms, if you prepare something in a certain state and then you measure it right away, you should expect that it's still in that state, right? So intuitively speaking, this induces a cycle, right? And where you have preparation and measurement, and you're back to square one, so to speak. And in generating that cycle, obviously there has to be some notion of time, right? So that's where we're going to have to make sense of the distinction between internal and external time. If we take this measurement operator and here perform some operations, we can write it as a unitary propagator from quantum mechanics, which again preserves information. It just leaves the state as it is. But with this little trick of the weak rotation, you can write it as e to the measurement up to a constant. And that, precisely encodes, at least morally speaking, what we just said, right? That this preparation measurement thing is a cycle. And more importantly, it gets rid of this t external time. And presumably in here, it's going to be replaced by some notion of internal time. We're going to have an internal time QRF that is sort of, quote unquote, the true local time as the observer perceives. I'm not entirely certain of the details, but now looking at it here, the beta, which presumably there's a beta and inverse temperature here. I think this is going to be intimately related to notions of thermal time. This has been explored in papers by Rovelli. How internal time QRFs and thermal time is the way in which the observer observes the passage of time. Those papers of Rovelli are linked in the Q&A, by the way, so I can also provide links later. I think there might have been a question. Should I stop?
Yeah, Dean, go for it.
Mm-hmm. I was curious about this because what I heard Chris start this session with was that he was going to try to help us understand when we are looking at something through a mechanical lens, so quantum mechanics. And to me, this slide was the way of addressing, as he said, his words were characterize information transfer in a quantum theoretic way, that the translation from H to M took the mechanics aspect out of the change or time piece. It was the purification, the most theoretical form of transfer of information, as opposed to holding up just the one ordered or sequenced or mechanical lens. I heard you ask the question, and I kind of smiled because I thought to myself, no, I understand why Anders is asking this question. It's, can something be both gripper in the conceptual meaning sense ontologically and gripped a physical object. And I think I thought, maybe I was misinterpreting, I'd like what your perspective on this is, that ability to go from H to M is what allows us to have both the mechanical and the theoretical, the transference in its purest sense. Is that being able to have both? Both can be true? Is that what
I think the answer is yes, for sure. Yeah. I much else to say here. It is true that you can think of the information transfer picture as an enlargement or an addition to the mechanical picture, and that I don't think that the mechanical picture has to be just thrown out completely. I think it's interesting to keep it to see how it can be recovered from the information processing picture. This reminds me, actually, there is an Italian physicist, I think his name is Cribella, and Dean, if you want, I can link you the papers later, who is very fond of the information theoretical approach to quantum mechanics and deducing quantum mechanics from first principles. And he has a paper, I think the title is Physics Without Physics or something like that, where he treats this whole thing as a big cellular automaton, and by taking appropriate scaling limits, he derives QFT, non-interacting QFT. So he says, okay, let me start with some axioms how information processing. I'm very, very loose here. Then get a cellular automaton out of this, and then take scaling and recover QFT, non-interacting QFT at least. So, start with a few axioms about information processing, recover mechanics from that.
Mm-hmm.
Does that add to your question a little bit?
Yeah. So all I'm trying to do is tie this back into some of the live streams that we've done in the past. And I know I use different language. I am not a scientist I've not studied quantum other than sort of in passing ways, but I do think that what this spoke to me about was something that I've always tried to include, which is that there's the figure it out piece, which to me is the conceptual and the meaning part that Chris talked about very clearly here. And then there's the outing of the figure. There's this sort of physical edge and boundary that if you don't have an awareness of both things happening concurrently, the preparation and the measure are a unitary, a sort of minimum of two state, then all bets are off in terms of being able to think of these propagators and operators and all of the ways that we're trying to explain the situation, they're off. So we have to have both. We have to have that sense that there is a transfer, but there is the mechanics. We have to keep both juggling all the time. So that's where this one particular slide was really quite both bias confirming for me, but I think it also, as you say, is going to open up a lot that July.
Yeah, I agree. I think this may be the most, important or mysterious, if you wish, slide.
Yeah, and it turns the pyramid, the conventional approach, here's a pyramid, into a top that can be spun, essentially with a Wick rotation, and it validates how information transfer probably gets short shrift in most of this quantum conversation, but it's probably at least an equal to the mechanical part. What order are we delivering this information in? So at that point, I'll stop. Thanks.
Yeah.
Thanks. Alexi?
Hi, can you hear me?
Yep.
I'm my mathematics teacher in high school used to say, "This is beautiful, but I don't quite understand it." So I wanted to I have two questions, but I'll start with this simpler one. So when Chris talked about the reference frame and said common language, I think in Shannon, common language is the alphabet. There's a receiver and sender and the alphabet that they share. And then Chris said this reference frame is a physical thing, like neurons or hands or mouth. And then I got lost because, if when I encode, I modify something on the hard drive, then the physical components of the hard drive is the reference frame. But, this is not the shared language then, So that's my first question. Maybe I'll stop here to really, I understand we're dealing in metaphors, but I want to understand that, the reference frame up or down, if Bob and Alice understand it similarly, then is that really physical?
I think the answer is that Chris would probably give a better answer.
Start from the beginning, Ander, go.
Is that both are true at the same time. I think Chris would give you a better answer, but the semantics or the shared language or reference frame has to have a physical embodiment, and that's a piece of hardware. It's a neuron or something. In this case, it's your free choice of the spin axis, and that's your reference frame. But at the same time, it's a physical piece of hardware. So reference frames are both a piece of hardware, but also a piece of semantics.
So if I take it from the language I don't quite understand to computer science, so if Alice and Bob communicate through a piece of memory, whether it's random access memory or hard drive, then Alice encodes something on that hard drive and Bob reads from the hard drive. So in that sense, they understand how to encode and decode, but they use the same physical piece. That's the reference frame. Would that be correct?
I might just add one again, continuing with the computer science. Let's just and the Shannon alphabet. Let's just say that these are plain text character encodings. And so they share the same set of character A through Z encodings that is reflected somewhere physically. And so if a message were sent from another letter, it wouldn't render properly. It's like outside, they couldn't differentiate omega from zeta because they only have the A through Z software pack. And so there's an informational distinguishment that's facilitated by the information that's classically inscribed on the screen, the memory, and there is an embodied physical as well as a semantic aspect to that situation.
All right. I think I'm getting closer to understanding. So to move away from computer science, if Alice is a painter, she took a brush, dipped it in red paint, and painted on the canvas red, and Bob has the same understanding of red as Alice, and then he looked at the canvas and read red, then it is both the physical, a mark on the canvas and the symbol of red, right?
Yes, and if somebody had red-green color blindness, their physical apparatus was not able to informationally distinguish, then they couldn't make this wick rotation into the quantum cognitive space. They wouldn't be able to detect that there was a red figure painted on a green background. Whereas
a key component here is that the reference frame is inside of the agent. It's, if you are colorblind, there is something physical inside of your head or your eyes or whatever that does not allow you to see the difference. So your semantics are affected ultimately by a physical piece of hardware.
Well, yeah, maybe I used a bad example because color actually is computed in the brain and color blindness is not necessarily physical. So, okay, but I think I get it closer. But, if I may ask another question, I get lost with the saying that preparation and measurement they have to happen both. And that when you prepare, or when you read, you modify. So I'm okay with the act of writing, the act of encoding. So when I encode something, such as I mark red on the canvas, or I write to the hard drive A, I modify the hard drive. That is true. But if I am asking a question, right, I am not modifying anything on the canvas. So in what way the act of asking the question or preparation is modifying the qubit? This is where I'm lost. Does that make sense?
Yeah, I think this is exactly the question I asked to Chris in the stream. So I can't quite remember his answer, but I think it was basically that they're completely dual pictures. Duality in the sense of, they're both two ways of looking at the same thing. It's kind of like, evolving time towards the future or the past. If you have time symmetry, you can do either. Yeah, so I myself, I'm slightly confused by but I think the answer is that they are same thing at the same. The picture of or am I preparing are just completely dual. That's I think. Well, do you remember that, Daniel?
Yeah. Okay, I'll give a different angle than the formal duality relationship. So let's think about our measuring device is going to be a carpet, and we're interested in whether somebody has walked on the carpet. So to prepare the carpet, we comb it very nicely in one direction. And I'm sure there's analogies there with the preparation of qubits in a quantum computer. But we're going to comb the carpet as an act of preparation. And then something is going to happen. Maybe it's a split second later, and so we're very confident that it should be still nicely combed. Or maybe it's going to be a whole working day later. But now we're going to take that probe, the tip, whatever it may be, and we're going to run it along the carpet. And we're going to measure the state of the direction of the fibers of the carpet. So if we didn't prepare the measurements, we wouldn't have a calibrated reference point to know how things had even changed. And so there's a cycle of preparing the apparatus through something like a calibration, or at least like a emptying of memory, to be able to then make an observation, and to have that observation have the kind of meaning that we would have expected. Like, purge the photodetector, make the measurement. Now you have to purge it again. That's the preparation. What do you think, Alexei?
That is a beautiful metaphor, and I dig that, except I think I heard Chris say that when you prepare, you make qubit into up or down, and this is when I'm lost. Because when you comb the carpet, you don't do that. You don't put the footstep on it. In fact, there may not be any footstep, right? And this is where I'm missing, I think in quantum physics as well, where if you measure, there's the cause and effect relationships are broken here for me. If in my act of preparation, I'm opening my canvas to read the message, but I do not know what the message will be, I'm game. But if he's saying that when I prepare, I modify the carpet such that it becomes either up or down, actually, not blank, but up or down, then I'm lost.
You have to comb the carpet up or down. There's no blank carpet. So you have a slate, you have an Etch-a-Sketch. You could either make all the pixels white, and then you'd be able to measure a message in the dark, or you can make all the message dark, or the slate dark, and then you could be able to measure something that was light. But you pick a direction of polarization in your preparation or calibration step, so that deviations from that can be the measurement.
So you're saying carpet is binary. Carpet doesn't have multiple states. Carpet can only have two states. So if I prepare it, I effectively put it in one of those states.
Well, let's say let's say we had the carpet at a 45-degree angle. Mathematically, we could describe that as a mixed state, and it may not be the most effective for measuring the movement of people across the carpet. But yeah, you could define it or comb it that way. It doesn't necessarily, if it were only a binary, it wouldn't be a qubit. Then it would be a classical bit.
Actually,
yeah. Under go for it, and then Dean.
Yeah, with I recall lecture, couple of slides more. We briefly talked about it like 10 minutes ago. By preparing, you are choosing an axis, and whatever you up or down in that axis. Now, that doesn't mean that the environment gets to do its own thing, right? And a superposition of outcomes, but at least you're measuring in that axis, right? So it's going to be either up or down in that axis. You can call it two pictures. And I just want to say a few words on graphic screens on the Feynman diagrams, and maybe clarify the question a little more.
Dean?
I found this really, really interesting. I don't know how metaphorically you could explain the carpet as a wave, but I think once you get away from the it's up or down, that possibility enters the conversation. And the only reason I wonder whether or not metaphorically the wave aspect of that can be included in how you're describing the carpet is that Chris spent quite a bit of time on the all possible paths argument, and in particular, and I love this, when Alice isn't looking.
Right.
Well, in that wave equation, how could Alice not be looking? That's what gets real. I mean, Alice could not be looking if it's binary, if it's or up or down. But if it's wave, it's a unitary propagator. I'm not sure how she takes her eyes off of this preparation measure thing that's going off all the time. So this is actually what I consider to be a feature or an opportunity or an opening, in the sense that from a strictly information transfer piece, not a mechanical piece, now not a physical thing, from an information transfer piece, maybe the carpet can be metaphorically understood as a wave, that the eyes of Alice or whoever's doing the preparing and the measuring, Bob, Alice, I don't care, Peaches, that there is actually a difference then between something that is exchanged and something that is informationally transferred. And again, I don't think that the four of us here sitting right now are going to resolve that, but I wonder if part of the difficulty in this is finding the physical metaphor that explains the theoretical transfer in such a way that it both breaks the symmetry and holds it. Because again, we're back to gripper and grip. We're back to figuring it out and outing the physical figures in the state that we're in. And we have to do both at once. So again, Daniel, you're the creative guy. How do you turn your carpet metaphor into a wave equation?
Maybe there's a subwoofer in the room, or maybe somebody is waving the carpet. But what
Right?
you said about the what is exchanged and what is transferred, maybe the transfer is the classical component. I don't know which one will be exchange or transfer, but one of them is the classical inscription. That's how many gigabytes were written or read to the hard drive. But what's exchanged, let's just say, are the semantics of meaning. And given an appropriate co-preparation, maybe only one bit needs to be transferred for the exchange of a message that was already triggered to be set off. And then also this entire discussion, it kind of strikes me as like the Cartesian duality of our time, but rather than mind and body, it's the physicality of information syntax and the metaphysicality of information semantics. And that's these kind of two worlds with their own physics and metaphysics that we're trying to connect. And it's like, similarly, well, how does the information world cause something physical? How does the physical cause something informational? And I think that the entire journey that the course and everyone is on is physics as information processing. That those as a qualified and distinguished but minimum of two set. Alexi?
Yeah. Thank you so much. Can you hear me?
Yeah.
I'm thinking out loud maybe, but I think the way to get closer to understanding in my head is to let go of the metaphor of asking a question, right? So if Alexi is talking to Daniel through Zoom and I pose even a closed question up or down, so I formulated the question and released it into Zoom space, and then I'm silent and I opened my listening to your answer. But you, Daniel, have agency to say up or down. I do not have any effect on whether you will say up or down, right? That's the difference. So me asking you a question does not modify the answer. You decide. Alice talking to Bob. Bob has the agency to answer the question, not Alice. And that's where I'm stuck. So I don't know if asking a question continues to be a good metaphor. Preparing the instrument for measurement is maybe better. And so, but actually Alice is not asking Bob. Alice is acting on a qubit, right? And qubit is a simple thing that can literally physically be up or down, I guess. And so that's maybe that's the answer, that Alice is not asking Bob. Alice does something to the qubit, and because qubit can be up or down, then that's no longer asking a question. Asking a question implies your correspondent can tell you anything.
When we're dealing with the very sophisticated process of natural language question asking, I think we're dealing with something that's orders of composition above the kind of binary ask. So I agree with that. It's almost like Alice prepares the photoreceptor. So its slate is refreshed. And then it's the photon or the light emitting object that has the agency to send the photon or not. I mean, maybe the preparation occurs and then no one comes back to check whether or not agency was even exerted. And I think when we really focus on like the nano probe, like atomic force microscopy, really tracing with a super fine tip over the surface of something or scattering x-rays, when we really think about the moment of information transfer, we realize like nothing comes for free. And I think that this question asking framework, other than really conveniently rederiving quantum mechanics in 1 hour, incredibly, helps us understand that we don't get to ask it for free in terms of time. We don't get to ask it for free in terms of energy. And we don't get to ask free floating questions where the question and or agentic responder are not involved already in a semantics. So I think it's calling attention to the components of an experiment or a question or an opening, but agree that it's not always as simple as a binary question, but in the special, simple basal case, it does start there. Ander, do you want to look at any of the participant submitted questions, if there was any that struck your fancy?
Let me finish real quick. I have maybe 5 minutes to wrap this up. So this I think is going to, at least in part, answer one of Dean's concerns. So the next thing we should very briefly cover, so let's talk a little bit about holographic screens, and also this is the paper on the physical meaning of holographic principle. So let's take a look at also this picture from that paper. This is the holographic boundary, and Landauer's principle and all these thermodynamic constraints on information processing necessitate the breakdown of this boundary in terms of free energy extraction sectors, memory sectors, and so on. And by the way, if you read the paragraphs around this picture, there's more details on how the time QRF is induced, but we'll leave that as it is for now. Dean, what I meant by this answering your concern was that you don't see how Alice can take off her eyes from the picture.
Yeah.
But that's precisely what's going on here, right? There's a sector that's being observed, which is a subset of these qubits that are being observed, but presumably she has the freedom to, say, hey, this sector, I declare as my observation sector, this I declare as my memory sector, this I declare as my free energy extraction sector. So it is because of these fundamental limits on the amount of information processing, it is not true that she doesn't have an idealized, Laplacian, if you wish, access to all the degrees of freedom. She can only observe a finite amount of stuff. So she is forced to take her eyes off at least part of the system, at least for a while, right? Because otherwise, all those energy and time constraints that Daniel was just mentioning, they're not. You have to abide by those. So, so a few things that Chris mentioned in the last lecture when it came to this holographic screen is, well, number one, that all the information exchange is mediated by bits here at the qubits at this holographic screen. This, in turn, enforces a finiteness in the information transfer, if you wish. There is not an infinite amount of information in finite space. Even if you were to pack it at Planckian density, which is presumably the limit that black holes achieve, it's still a finite amount of information in a finite amount of. So if you have finite constraints, you are taking. The other is the following, and again, Chris will deal with this at greater detail in perhaps lecture 5, I think, maybe 4, but it's the notion of emergent spacetime, which is that A and B separately. So you think of, these are presumably the internal degrees of freedom, what's going on inside of A, Alice at an abstract level. There may not be a notion of a space, but, the notion of space emerges at the boundary. And that's not easy to explain. I think presumably has to do with and stuff like that. And I don't know the full details myself, but for now, that's one of the key things that Chris mentioned, which is that an agent, may not have space, but it may emerge boundary. And the last thing, and I'm glad to see that this was mentioned already, so it saves us time. I don't have to say it again. It'll take us a minute. This 5 minutes. And this again answers your...
Can you just turn off your video, Ander, just so you don't have lag?
Yeah.
Thank
One
you.
second. You guys, can you hear me?
Go for it.
Okay, so this notion of the Feynman diagrams, right? So what is this whole thing about unitary evolution or propagation? The scattering picture, as Alice preparing a vector of her boundary, right, and writing it into her memory, and then measuring it at some point in the future, right, requires that you consider the possible what happened to that preparation. Okay, so if there's some amount of time passes, you prepared, your state at time t, you look at it again at time t plus dt, you have to take into account all the possible histories. It's literally itself of the system, or at least that part of the system, right, Dean? It's just saying I prepared it here. Now it's up to B what happens until the next time I look at it, up to the environment. So I have to, in that unitary evolution, I consider all the possibilities, right? And that's exactly, the Feynman integral flow. So let's just look at the concluding slide, and we'll leave it there for now. Then we can open up the discussion. So there's two things that are now. Well, where was this? Yeah. Yes.
So
Go ahead.
yeah, so I understand, or I think I understand. I think I understand that if I'm looking at on, or if I'm attending to on, I'm not looking at off. What I saw in that wave thing with Feynman was I could also be looking at the switch where the two different places of on and off exist. And when I'm looking at the entire switch, I'm not looking at one or the other. I'm looking at that basal, as Daniel described, that basal opportunity of both. And I think that on that, I don't know how that ties in with reference frames, but on that level that says, I'm now looking at all possible. In that moment, I don't think, at least from that perspective, that reference frame, I'm zooming into a on or off binary choice decision branch. I'm still at that place where the preparation allows for both. I'm literally not taking my eyes off at that place. So again, I'm not arguing with you, because what you described and the image that you brought up, all that is bringing it down to a granular level and saying, if I'm paying attention to this, I can't be paying attention to that. But if I physically, from a transfer perspective, back up so that I can see both possibilities at once, I don't know that I'm taking my eye off of either. That's the only thing that I was bringing up. Now, of course, Chris will probably hear this and go, Dean, you got to go and rethink this whole thing through, which is great because I'm here to learn. But that's, again, if I misspoke about what I was trying to say, it wasn't because I don't see those moments when I'm directing my preparation over here, and that's going to give me one kind of measurement versus if I'm taking in a larger time frame and now, or larger spatial frame or larger holographic screen. Like, I don't even know how to describe it because I just don't have the words for it yet. But there you go. I just want to be clear that I don't think I'm confused. I just want to know the difference between when I'm looking at on or off and when I'm looking at the entire switch. That's all.
I'll add one point on this slide. It goes back to some of the earliest points that Chris made about the ontological primacy of communication. Space and time arise from communicating agents. Communicating agents are not something that we have to squeeze into an a priori spatial temporal framework. So quantum mechanics, saying here on the slide, is about measurement, not mechanical motion. So we don't need to wait around or speculate as to how, from the, quote, mechanical or physical hard drive, measurement arises or happens. We start with the measurements occurring, and then different kinds of sophisticated agents can conceptualize of movement through spaces and times. And this also relates to Bayesian mechanics as a mechanics and a physics of movement on information geometric spaces. And so the physics can be projected by appropriately prepared agents, but we don't necessarily need to wonder about how that agent fits within a mechanical setting. And I guess this is where humans are with the I am a strange loop, Gödel, Escher, Bach, gripper and gripped mystery of being able to see it multiple ways. Andre, do you want to go to the questions?
Yeah, let me just say closing remarks here. I think what Chris is punching line of the paper, free energy principle for quantum systems, which is, morally speaking, it's similar to relaxation to thermodynamical equilibrium, which is that if you have an isolated bipartite quantum system, A and B are going to tend towards reference frame alignment and therefore entanglement. And these two things are basically very intimately related. So by aligning the reference frames, you'll get A and B will be driven towards maximal entanglement. So should I take a look at the questions and we can open the discussion? Yeah. So if you guys have access to the Q&A, there's been more questions in the last, bringing you guys' attention to a few of them. This is where Chris links to the papers of Robelli, which I mentioned earlier in passing when we were talking about the preparation measurement cycle and the notion of thermal time or subjective time, if you wish. Somebody brought up this remark that performing some calculations here, you can relate T time to a change in the volume of phase space, or more precisely the amount of available states in the state space, with the log and whatever, with respect to the energy, right? And so this restates the idea that we're talking about earlier, right? Like in your intrinsic subjective time being this d as the iterative a thermal time, basically speaking, that is observer dependent. So that's a good question to take a look at. There's another one. What is meant by local free of choice? This is a very good answer too. Local here means at some boundary, right? Isolated systems are idealized by definition. There's always going to be an observer interacting with an environment. So a purely isolated system is an idealization. So what local free choice means here is exactly what we said earlier, right? That you get to choose the spin axis at the boundary qubits. And there were some nice questions relating Markov blankets to the scattering picture. So this one, for instance, is also worth a look. So somebody, brought up this, very good point about the scattering matrix. The scattering matrix is, by the way, let's not think about it mathematically. Just let's think about it, the picture, right? You imagine two particles that are interacting, and far away, they are free, right? They are spatially separated and interacting free particles. Yeah, and somehow at some point they come to interact, right? And then you'll have to write all the Feynman diagrams for all the exchange of bosons or whatever the interaction is. And that's how you would compute the amplitudes for the scattering process, right? How those two particles that were separated came to interact, and then they go off to infinity again. Chris here brings up the point that in a sense, how you define a Markov blanket is in the opposite direction, right? Markov blanket, at least in the graph theory sense, you start with a node, and the Markov blanket is just the set of nodes that separate, in terms of conditional probability, that node from everyone else, right? And then you can have edges, which are going to be directly causal networks. So acyclic, no cycles, directed edges. That's how the graph looks. And you build up. So essentially, you're taking the opposite picture, right? You start with a node, which in this case would be the interaction, and then you build up to infinity. As opposed to in the scattering picture, which is like you start with particles not interacting at infinity. You see how they go off to infinity again, and then the interaction is in the middle. So that obviously the answer is a bit more precise, but it's worth taking a look at. And this is an interesting one too. Of a symmetrical input-output bandwidth. So again, if you think of it as a graph, nothing is constraining you to say that you're going to have more incoming errors than outcoming errors into the boundary, right? That's just the way it is. If you think of it as a graph, there is no symmetry imposed. The only natural sense of symmetry would be energy conservation, and that's exactly what Chris says here, right? Which is that. And I'm not sure myself how you relate it to a conservation of, not quite information, but I wouldn't know how to phrase it myself. I would just take a look at the question. But basically, no, there's a priori nothing that necessitates symmetry in input-output in Markov blankets. But if you are to talk about any sort of symmetry, the natural language would not be in terms of incoming versus outcoming errors, but rather energy conservation, which we saw is a close cousin of information transfer, right? Because of the minimal requirements for action to rewrite a qubit. And the last question that I would like to bring you guys' attention to, I mean, all of them are great, but we have finite resources and finite time, unintended, would be this one, okay? And I'm not going to go into too much detail, but this is again about the local. Wait, no, 1 second. So turn on my camera, by the way, Daniel.
Go for it. And also, people can see all the questions on the website,
right,
and submit their own as well.
Yes, for sure. So now I lost track of the question that I wanted to show you guys. I think it's this one over here. Yes. Yes, exactly this one. So by the way, all of them are good. Even this one, the holographic principle, does it make it easier to compute any physics problems? Well, please take a look at Chris's answer, but all I can say is that these ideas of holography I'm not an expert, I'm not a condensed matter physicist, but they're used all over physics nowadays, not necessarily just in high energy. I know that condensed matter theorists use them all the time. So the answer to this is an emphatic yes. The holographic, at least ADS-CFT is used all over. But again, I'm not a physicist myself. So this is the last question I wanted to bring your attention to. And here, Chris, this may be the one worth taking a look at in terms of, in order to answer all, the earlier speculations that we had about time. Internal clock here. Somebody asks about synchrony and, just the perception of time with respect to external clocks, I suppose. And Chris here answers that at the end of the day, even if you're using an external clock, everything that you perceive outside at the end of the day has to be in terms of an internal clock. Any information incoming, you're going to have to, make causal sense of it. You're going to have to write it into a memory in terms of an internal clock. So you're never going to be able to, so to speak, increase your precision of the passage of time by taking an external clock even if you think it's more precise than anything you have inside. I think that's basically what his answer amounts to. And this is more related to, all this frame halting problem stuff, where because I'm never, as a system, you're never going to give an infinitely precise, I'm speaking very loosely here, an infinitely precise description of yourself. You're never going to, morally speaking, again, that's what it amounts to. You're never going to be able to outdo your internal clock by trying to leverage something external, like an atomic clock, that even if you think it's more precise, at the end of the day, your own subjective perception of information will depend on internal clocks. So we can open up things. Any concluding remarks, and any other, Alexei or Dean or anyone else who may have joined? I don't have anything else to say at this point.
I mean, where or when are we? We had session 1 with a real big historical overview.
Mm-hmm.
Section 2, we focused on the measurability question, which is answered with a question, and we talked about some of the constraints of question asking, namely that it takes time, it takes energy, you have to ask it to somebody or something on an interface, and it has to have a semantic quantum reference frame. And this is dovetailing with the free energy principle, of course, because the free energy principle, as it says in the syllabus, to what does the free energy principle apply? And Chris says everything measurable. That's why it's a theory of everything that we choose to measure and model, not ontological statements about what is. And then where are we heading into in session 3? Have you looked ahead, Ander, or do you want me to read what's in the syllabus?
Please do. Yeah.
Yeah.
I think basically my short answer to that, and possibly my full answer also, is that it's just going to take care of the loose ends in this lecture 2. So this lecture 2 is a warm-up to the real thing, which we need to talk more seriously about reference frames in order to get the precise picture of this quantum measurement process.
Yeah, it says that session 3 will introduce the idea of quantum reference frames and the representation using hierarchies of binary classifiers. These formal structures provide a semantics for measurement and hence provide the basis for a theory of meaning for interacting agents. The language of QRFs allows a particularly straightforward and intuitive definition of variational free energy, and so allows a fully general quantum formulation of the FEP. We will see that the FEP is a classical limit on the principle of unitarity, the fundamental principle of quantum theory.
By the way, Daniel, can I? I'm not sure if you're busy, but I just got an email from Chris. I think he may be watching us, and I think he's just confused about the link. So, Chris, I don't know if you're there still, but do you think it's worth it? Will we send him the link real quick? If he can come for a few minutes?
Yeah,
or
I will.
You have to go.
Oh, I'll send Chris the Zoom link now. So
yeah,
hold on to your qubit, Chris. We're coming.
Yeah. So let's give him a few minutes. Maybe he's still watching, and he'll answer the questions better than I could.
Well, Daniel is sending him a lifeline. Can I just from the rookie perspective on this? Session 1 seemed like there was a big time window, like the historical piece over using an external clock and a timeline. This one felt like the parabola and the up or down and the entanglement was almost instantaneous in terms of that Planck length that we were really holding up as comparative to that timeline, that chronological timeline. And so I'm guessing that now that we've established those two as different, where does that go? But again, that's just the rookie's view of things.
Hey, Chris, welcome.
Yeah, hi. This was a very interesting discussion, and it's given me some pointers as to what to emphasize at the beginning of session 3. But I can say in response to Dean's question that the time when Alice isn't looking is the time during which Bob is making his measurement and then his next preparation step. So if you consider again that slide that shows sort of the Feynman representation of what's happening as this unitary flow, that's what Bob is doing. And I think Ander said that. From Alice's point of view, Bob is just some quantum system, and she's banged on that system by asking a question. And now that system is doing something or other that she can't see until it, i.e. Bob, bangs on his side of the screen, and she gets some information by making a measurement. So she may be not looking for a very short period of time, right? I mean, according to her internal clock, she's not looking for just the time it takes for one of her internal ticks to take place. But in general, we're not saying anything about how long that time is, right? If you think of this in a scattering theory way, then we're talking about the time between two protons leaving the rings on the Large Hadron Collider to the time that all the stuff that comes out of their collision is measured by the detectors, which is a nanosecond or something like that, some very short period of time. So just think of that interval as the measure of the intrinsic time dependence, external time dependence of the interaction. Someone has to do something, and then someone else has to do something, and there's a gap between what the first person does and what they see in response. Let's see, what's the other question? The other central question that came up today was the question of why observing something requires action. And of course, in the classical picture, observing something doesn't require any action at all. The event just happens. And this is the fundamental, if you will, distinction between classical and quantum theory, is that making an observation in quantum theory is taking an action on the world. And there's a lovely metaphor that's not correct in detail, but it's very useful, I think, conceptually, which Heisenberg came up with to try to explain his uncertainty principle to his classical colleagues. He said, look, suppose I'm trying to see a very small particle and measure its motion. I have to have a microscope to see this particle. And to measure its motion, I need to light it up. I need to shine some light on it. And those photons of light are actually impacting the thing I'm trying to see. So the act of observation itself requires banging something into an object. And when we're just looking out at the world, it's the sun that's banging the light into the object, not us. But we can sort of merge those two systems together because it's the sun that's taking the action that lets us get some information. but the sun is perturbing the things that we're looking at by banging photons into them. And I think that picture of Heisenberg's is what he used to actually derive the uncertainty principle in terms of momentum and position, because banging something into something is transferring momentum to it. Photons transfer some momentum to the tiny particle in the microscope, and that perturbs its position on the microscope stage, which is precisely what Heisenberg is trying to measure. So that's his point in that analogy. Observation itself always takes action, and that's why observation and preparation are duals in quantum theory, because they each require a minimum 1 unit of action. And I think, Ander, you said the duality can be thought of in terms of time invariance, and that's exactly correct. Preparation is just measurement run backwards,
Right.
and vice versa.
And if you let me say a few words, I think this also answers my own confusion and the question that Alexei posed earlier, which is this duality between preparation and measurement. In your picture that you're bringing up, Chris, with Heisenberg, by shining photons on a particle that I'm trying to observe, these pictures of preparation and measurement are dual, because in doing so, I'm constraining the system. In trying to measure it, I'm constraining it. So in me trying to gather information by shining photons on it, what I'm really doing is I'm constraining it. I'm just saying you can only take this momenta or position. Would that be correct?
Yeah. In fact, in the microscope example, it's particularly clear. You're bouncing a photon off of the object, and then it's that photon that you're detecting.
Mm-hmm.
Right. Oh, there was one other question that can be answered quickly. It was the question about what's the reference frame that Alice is using when she's measuring up or down, measuring her spin up or down. And of course, there's several reference frames involved here. So let's work inwards in a real system. Alice is sitting here. She's got a Stern-Gerlach apparatus, which is a vertical magnet apparatus. And she's measuring the spin of an electron that's traveling through this Stern-Gerlach device. And what the Stern-Gerlach device does is orient the spin with a magnetic field that's not homogeneous, so it ends up pointing physically up as it comes through the apparatus. So how is that apparatus oriented? I mean, what defines the up direction for that apparatus? Well, in the practical setting, what defines that apparatus orientation is the Earth's gravitational field, right? We're here in the laboratory, and the Earth's gravitational field tells us what direction is down. It's toward the center of the Earth. And so up is away from the center of the Earth, and that's what defines the axis for the apparatus, which is a great big piece of metal, so it's very responsive to the gravitational field. So now we can ask about Alice, right? Alice is also embedded in this gravitational field, and she also can detect the gravitational field. She can tell which way is down toward the center of the Earth by the force acting on her feet. And that measurement is taking place in Alice's brain. So in Alice's brain, there's a representation of which way is up. And that's the internal reference frame of Alice that lets her do the experiment. You know, if she was freely floating in space, but the apparatus was anchored to the gravitational field, she wouldn't be able to tell that it was anchored to the gravitational field. And that's the point that Einstein makes in all of those experiments where he has observers flying around in spacecraft, that they have to have their own reference frame. What Einstein didn't emphasize was that reference frame is in their head, right? It's encoded by their nervous system. I think it was Daniel who said this exactly correctly, that the physical object in her head, the actual neural network that tells her which way the gravitational field is itself a semantic object. I mean, that's what gives the word up and down meaning for Alice. And what do I mean when I say the word meaning? I mean, it lets her take some action. Semantics boils down to actionability. If it gives things significance. And this was the point that Bateson was making when he said differences that make a difference. For an organism, something is meaningful if it actually makes a difference for what I can do in this world that I'm trying to survive in. So I'll leave it at that. But this is very, very useful for leading off the next session. So thank you very much for all of that discussion.
Awesome. Thank you.
I guess if I could say one thing here is that, let me scroll back up to the 3 points early in the slides. Differences that make a difference would tell you that you require action to perturb a system and measure. And then the semantics or the contextuality that may be encoded in the nervous system would tell you what is the difference that is being made. Would that be correct?
Yeah. Right. What tells you that there's a difference there? It's what you're able to detect and represent internally.
Oh, it's almost like step 1, do differently. Step 2, you have to ask it to a different thing. And then 3, you need the semantic frame that makes A and B different. Differences all the way down. Well, we will transcribe this and fix the few patchy moments. Ender, we'll work together on updating the transcript so that everybody who wants to be well prepared for the measurement of the 3rd lecture will be absolutely in place. Thank you, Chris, for joining. That's a fun cap to this discussion. So,
all right. Thank you.
See you all next time. Bye.